All right, let's continue. I'm sharing now a slide. I still wanted to discuss briefly with you regarding the helium atom. Now, there's a famous quote by Kelvin, who remarks on how we actually would determine if we understood something. He describes sort of a necessary criterion for understanding if you cannot measure it in numbers, if you cannot express it in numbers, right? Your knowledge is of a meager and unsatisfactory kind. I really enjoyed that quote. I think it holds, right? It doesn't mean your understanding is zero, right? It could still be very, very deep understanding, of course, and strong intuition you can develop. But in some sense, it is, by construction, it is meager and unsatisfactory. You cannot quantitatively predict anything, right? So that's what it implies if you cannot put a number to it. In terms of quantum mechanics, of course, you can now ask, right, what is the right understanding of quantum mechanics? We discussed this at the end of the theorems and postulates, right? And so there are many interpretations, right? There's a Copenhagen interpretation, there are many worlds interpretation, consistent histories. There's an ensemble interpretation, there's a hidden variable interpretation. So all of these are on the table, if you wish, right? But one thing is sure, they might have their merits, for sure, right? But there's that interpretation where you actually calculate something that deserves special attention. So when I was an undergraduate student at ETH Zurich, my professor Martin Quack, he once said this in a lecture, that we only understand molecules once we predict their properties with quantitative accuracy. Okay. My friend Nicola Masi from EPFL, he also rephrased this into saying, shut up and calculate. Okay. So you can think endlessly about Schrödinger's cat and whatnot, but at the end of the day, you want to quantitatively predict the rate of your reaction, or you want to quantitatively predict the yield of your reaction or the equilibrium constant and so on, right? And if having a full understanding of Schrödinger's cat and what it all implies in philosophy is a whole different business, which is not the topic of our course, for sure. So coming back then to helium, when we calculate, we discussed the energy, right? And you see now the energy, let me switch on this pointer. You see here the energy calculated by a scientist called Hilleras in 3 terms, and this is the value. This is very close to the experimental value we discussed, right? Now this one is basically the same as the experimental value. You see here the significant digits in bold, and the normal digits are sort of uncertain, right? There's some variance on them. Now in 66, these people contributed this number, right? And you see it recovers everything, but we go further, right? So, and this is a problem, right? We can, what is the true number now, right? And you can push this game further, and it was, right? So this is just 2 electrons surrounding two protons in the nucleus. The helium atom. Right? You see here the more and more papers, and then until the year 2007, so there's maybe by now there's a new paper, but you see people are killing the helium atom. So for these to have so many digits calculated in terms of significant digits, to have a number with so many significant digits, you need to devise special logarithms and special compilers, and you cannot use standard numerics. Okay? So this tells you something. In which year did humanity understand the helium atom? Right. So now you see that this definition of quantitatively calculating or predicting something is insufficient, right? It also implies the need for some criterion how accurate you need to calculate something, right? So how accurate do you have to be? And then do you reach that number, right? That would really then determine if you understood it for that particular purpose. You might, for instance, think about setting up a thermochemistry experiment, right, with the calorimeter or something like that. Well, these measurements typically have an error bar of something like 1 kcal per mole, right? And so to calculate things beyond 1 kcal per mole is simply not necessary to design your experiment, right? It would be a waste of time. If, however, your experiment was a spectroscopic experiment with spectroscopic accuracy where you measure individual wave numbers, well, then you have to be more accurate than 1 kcal per mole, right? In order to have understood the problem sufficiently well, such that you can predict it with sufficient precision. All of this is just the helium method. So there was a famous quote by a computer scientist who then also got a Nobel Prize in physics, Eugene Wigner, who said that it's nice to know that the computer understands the problem, but I would like to understand it too. And that's very true, right? This is why we are discussing the variational method. This is why we are looking for gradients, right? And we are discussing the gradients. You have to understand what's happening, right? That's the point of a university education. And so this is, we should not forget about that. Yes. You have to know how to program, you have to know how to use the programs, but you also have to know and understand what's behind them, right? And so this is sort of a set of citations, and I'd like to leave it with that. And I'd like to now return to our main lecture. So let me share our slides again. And I'd like to go to the second subchapter, which is called the secular equation. A secular equation is related to the characteristic polynomial. It's what you get by doing linear algebra with matrices when you have to diagonalize them. And it turns out that this is the more general, the generic way to design algorithms that solve the variational problem for you. Okay. So an example is 1 and 2, which we just discussed. We are sort of doing this by hand, right? And once we optimize the C coefficient, then the nuclear charge, right? But as we go to larger systems with more electrons, this proves difficult, and there is a nice, very elegant and efficient way of doing this, which you have to learn about, right? And this is what we are endeavoring now to do. So we start out by saying we do a series expansion. And this you've seen so many times now, so I hope it's very clear what this all entails and why we can do this. Right. So we assume that this is a complete set, right, of n eigenfunctions and so on. If it's not, it's going to be an approximation thereof, right? So that's fine. But this is where we are coming from, okay? So it's all real. They are linearly independent. Which we guessed. Okay, so there's a bunch of these functions. And so our job is now to find the coefficients to be found via variational theorem. Okay. Now, we should, before we proceed, so these are not necessarily eigenfunctions. So we have to discuss one thing, namely that d tau simply this. And this, if our functions are eigenfunctions of the Hamiltonian, right? Then of the Hermitian, the Hamiltonian is Hermitian. Then this would be just the Kronecker delta. But in general, if we just guess a bunch of functions, this is an ansatz, right? So let me emphasize this here. This is our expansion, just an ansatz. Since we do not know this for sure, we should write this as sjk, which we call the overlap integral, also known as overlap integral, and hence ik jk cj ck sjk. Okay. So this is not necessarily equals delta jk, since we do not assume fi to be eigenfunctions of H. Now, why don't we assume that? Well, usually it's not so easy to know the eigenfunctions of the Hamiltonian, right? So for the hydrogen atom or the quantum harmonic oscillator, this is actually okay. But for more complicated systems, these eigenfunctions in general, we do not know them. So we'd like to forego this assumption, and we do that by introducing the overlap integral. All right, so what do we do now? We have to calculate our E tilde. So that's d tau phi h phi, and hence this is j k cj ck, just coefficients, d tau fj h fk. And now we define this integral, since we don't know what the result is of h operating on f. We define this as a matrix element, as an integral, which we call hjk. Okay, so this is nothing else than j k cj ck hjk. All right. Hence our E tilde, which henceforth I would like to abbreviate as W. Say E tilde is identical with W equals phi h phi over phi phi is the same as sum over j, sum over k, cj, ck, hjk over sjk. Oh, sorry. Over j, k, cj, ck, sjk. All right. So far, so good. Now I simply pull the denominator from the right over to the left. So this means W times J, K, Cj, Ck, Sjk must be equals J, K, Cj, Ck, Hjk. All right. Now we're going to differentiate with respect to our coefficients, right? So differentiate with respect to Ci. Okay. So now I have to you really have to pay attention now. So far, we have two indices, J and K, okay? Why do we have two indices? Because when we expand our wave function, when we want to calculate the expectation value, we have to multiply it again with the wave function. So we have two sums, right? And to get all the cross terms, you need two separate indices, J and K. And now we're going to differentiate with respect to the C of a third index. All right. So you really have to keep track of this, that you don't confuse them. Right. Right now, three indices, I, J, and K. All right. Now we have here basically on the left-hand side a product of two terms, right? So this means we should use the product rule. Ci W times the sum plus W times the derivative of the sums equals the derivative of the sums on your right-hand side, okay? So this was okay, everybody agrees? Now let's call this term A, this term B, and this term C. And don't forget that A plus B must be equal C. All right. We're going to discuss these terms separately because they're going to be a little bit lengthy and it's going to fill the page too much. But A is simple, right? A must be 0 since ECI W must be 0 since this is what we impose via variational theorem. Okay. So A is taken care of. But what about B now? Let's look at B. So in B, we have the derivative of your double sum Cj, Ck, Sj, K. All right. And now we pull in the differentiating operator into this product of coefficients. Okay. Sjk does not depend on the coefficients, so we pull Sjk in the front, and then we have the differentiating operator working on a product of two coefficients. So we have to use the product rule again. So we derive with respect to Ci, Cj, and we have to multiply. Now let me write this differently. It's a bit messy here. B Cj Bci Ck plus Cj Bck Bci. Now the coefficient, one coefficient does not depend on the other coefficient. They're supposed to be linearly independent anyways. So these coefficients will be 0 in all cases except when I equals j, and in this case when I equals k. Okay. Now this means we have on the left hand side ij, and on the right hand side ik, and we can write our sum for these two terms as jk ck, and now your delta ij, and then again same sum is jk. So we just factored out the bracket, okay? Cj delta ik. These are two sums, okay? Now, because of the Kronecker delta, one of these summation symbols is going to die in either case. So this means only k, ck, s, ik survives, and here we have j, cj, s, ij survives. Right? Now I and k, j and k run over the same indices, so you can pull this together. It's twice. Doesn't matter how you label this, right? They both run from 1 to n, 1 to n. So you should see that this is nothing else than 2 times the sum, and now let's just pick k, Could call it also J, doesn't matter. Okay. Is this clear? So this is what happens to your B, right? And then we should discuss what happens to C. Now, in the case of C, we proceed exactly the same way, only that instead of S, we have H, right? So I can write in complete analogy dCi of some Cj, Ck, Hjk must be equals to sum over k Ck, Hik. Okay, so if we now make use of this, our equation A plus B equals C becomes 0 plus W times 2 times sum CKSIK equals 2 sum CKHIK. And we get this equation for every coefficient I with respect to which we are differentiating, right? So this is a set of equations you're looking at, right? So this is true for all I equals 1, 2, and so on, n, right? Now, the 2's, of course, cancel, and we can rearrange this equation in a more compact way. If you look at the summations, right, they both run over k, right? And so you can factor them together, right? So what we'd like to write instead now is that 0 must be equals sum over k equals 1 ck. And now what we have here is we pulled things on the right hand side. Ck must be multiplied with Hik minus Sik times W. Okay, so this is a very nice compact form which meets your condition. This is the condition that your gradient must be 0, right? This is the minimal, the gradient equals 0 condition from the variational principle. Again, for all I, let me write this, corresponds to setting gradient equals 0. Okay. Now we have this for all the i's, right? So we have a set of equations, right? So let's write this out, this set of equations. Right? How does it look like? Right? Well, so we start out with H11 minus S11W times C1. And now we go to the next K, right? So H12 minus S12W times C2. And so on and so forth until we hit H1N minus S1N W times Cn. This thing must be 0. Okay. Now that's for I equals 1. Now we go to I equals 2. H21 minus S21 W C1 plus H22 minus S22 W times C2 plus H2N minus S2N W Cn equals 0. I equals 2. Right? So you can easily see at some point when I equals n, you arrive at Hn1 minus Sn1 W Cn, C1 plus Hn2 minus Sn2 W times C2 plus until Hn minus Sn W Cn equals 0 for I equals n. Okay. So now we are back at 2 indices, right? One index, the K index, is along the row. The other index, the I index, is down the columns, right? And so for each row, you have a different I. Now, if you look at this equation, it looks like a matrix being 0, right? An n by n matrix equals 0. If you look close at the structure of this matrix actually looks as if you have the difference of 2 matrices. You have something like matrix A multiplied with a coefficient vector C that is equal to 0, where the matrix element A IK is simply HIK minus SIK W. Right. So if you insert this AIK into your big matrix A, and then you do the matrix multiplication with the vector C, you recover exactly this set of linear equations. Okay. Now, actually, let me call the matrix element small AIK. So it's also a common convention that we give small case letters to matrix elements. Now, this would be the matrix notation. Or you could also, which is sort of identical, simply say sum over your K, matrix elements IK, CK equals 0. That's basically the same as up here. Now, there's something which typically you do not learn at high school. And it's a trick from linear algebra. It's very well established. It would be nice if it was part of the high school curriculum. I don't know why it's not. It's crucial to do the next step. And this is basically what we do to determine your W. Okay. Now the trick is the following. So for your coefficient vector C to be non-zero, that means for the non-trivial solution, one can show, you're not going to show it, right? But I really think it should be part of high school math, but it's not typically. One can show that the determinant of the matrix before of A has to be 0. Okay, so this is a really important step, right? Without this step, you will not understand how the variational theorem works in practice. Okay, so you have to put this in your brain somehow. Okay, if you have a matrix times a vector equals 0, there must be the determinant of that matrix must be 0 too. Now this gives us a new equation, right? And that's really so crucial, right? Whenever you get a new equation, a new condition, then you can solve for something. And we're going to use this to solve for the W, right? So this means this is the same as saying determinant of AIK, right, equals determinant of A. There are many different ways to write determinant. So don't let yourself get confused by this. This equation must be 0, right? Can impose this. And then hence we can solve for W. Now, when you have a determinant, right, you have something like a characteristic polynomial. Right? You can also view this as a characteristic polynomial. And the solutions, and that's also known as a secular equation. We solve for omega as roots of characteristic polynomial, also known as secular equation. Now, solving for the roots of a polynomial function, this is something you've learned in high school again. Okay. So apart from this determinant trick condition here, there's nothing you shouldn't know from high school and from what we've discussed so far in the semester already. Because of all this, we also call this the secular determinant. Okay. Also known as secular determinant. And when you overhear Mr. Trestman on the corridor talking to his buddies, if they have already solved their secular determinant for this or that problem, that's what he's referring to. Now, this approach, you can imagine a matrix like this, right? An equation like this, you encounter all over physics, right? Not only in chemistry. You also encounter this in astronomy, you encounter this in fluid dynamics, you encounter this in economical theories, and they always use the secular determinant, right? So it's nothing specific to quantum mechanics. So don't go around telling everybody that quantum mechanics is so complicated. It's not, right? This is all over the place. The world is complicated, if you wish, but it's not really so complicated that you just have to memorize that this determinant of this thing must be 0, 2. All right, any further questions?
Sorry, I just can't read what letter is this. Is this an L below the A times C equals 0?
Where?
Below the bracket that you surrounded around A times C equals 0.
Right. Oh no. This is not an L. This is just an arrow.
Oh, okay.
Sorry. It's just a different notation. I'm sorry. I shouldn't. Just a different notation. Same thing. Okay. Sometimes people like to write it with a sum like this. So there's also something known as Einstein's notation, where people drop the summation symbol altogether, right? So unfortunately, there's a fair amount of jargon in textbooks and journal publications, and people don't really agree on just one notation. So my philosophy then is to basically show to you on various occasions the various ways people like to write things.
And can I just see where this arrow comes from on the right?
Oh, sorry. This is the same as these two expressions do the same thing, right? If you define up here your AIK, right? Then you recover the same expression as above.
Oh, I see. Yeah. Thank you.
But we first said, I showed you basically where this AIK comes from, right? By writing it out explicitly. And then you see it has this matrix times a coefficient vector form. That's why you would like to define this AIK coefficient. Okay, these AIKs are just the matrix elements of this A matrix, and the determinant of this matrix must be 0 because of this box, right? And this box must be 0 because of our variational principle, right? Which we said here. And we have this, and then here in A, we said this is 0. Okay. And then when you walk down here, you arrive at this AC equals 0. So this encodes the variational principle. All right. So what we have now is that you get the determinant with these matrix elements, I can also write it like this, right? It generates n solutions Wj for n states. Okay, remember your W is your energy. And basically what this means now is that you get n roots, which you can solve for omega, for W, right? And these W's correspond to the energy levels in your spectrum. Okay. So you have this, the dimensionality of your matrix A, the I's and the K's, right? And now you take the determinant and then you get again n solutions for the roots. Those are your J, right? The J solutions. So we are back at our three indices again. Right? You can rank them. Right? And then you have your energy spectrum. And because of variational principle, any ansatz you do delivers a different W, right? Which will be above, right? It's the E tilde. So the true energy is going to be below W1, below W2, below W3, and so on and so forth. All right, we continue this discussion tomorrow. It's noon. I have to leave urgently. Please, for all questions, get in touch with the assistant or let's discuss it tomorrow. Thank you and goodbye.